magic trash can, microprocessors for full stack developers. Let's try something. For the not so elders among us, this is a telephone. It used to be connected to a plug in the wall, and you could dial a number by that rotary dial. And I will totally fake that now because it's in German, but I will just pretend it's I had that in English. So let's see if a we works. So let's dial a number. You wake up. There's this strange sensation in your left toe, a kind of tingle or something. You don't know what this should mean. So what do you want to do next? Dial 901 to just pull your blanket over your head again. Dial 910 to have a cold shower. You're in your shower now. Warm water is running down your back, and suddenly you realize there's something. I've forgotten something. You jump out of the shower, grab a towel, and to learn what's your realization, dial 999. You realize, oh no, today is the day of my clojure talk, and I still have to finish some slides. I need to update some hardware, firmware. I need to reinstall the internet, update Node.js and everything, so you jump into work right away. So I'm sorry, that was totally fake, but if you want to try it in German, you can do later. There's an actual story in that film. So, microprocessors for full stack developers. What's the motivation? Not only that thing, but also I love keyboards and I love building keyboards. I can only recommend not starting that hobby because it's A, expensive, B, takes a lot of time, and it's complicated. I like blinking lights. You see a nice fire simulation here built with a microprocessor and some kind of LEDs, and I own a 3D printer, and yes, that's the actual situation. I took that picture before I left for conference. And well, they are also driven by microprocessors, and I'm pretty much sure that's not how you should do that. So, head on. I changed my talk, and I included that picture I took yesterday evening. Arcade machines, pinball machines, all those whatever Super Mario games are driven by microprocessors. Most of them are super, super, super non-powerful compared to today's standards. When you go and buy a random microprocessor nowadays, it will have hundreds of times of the processing power than those old machines, but still you could achieve awesome things. So how do these work? Just a quick wrap up for everybody who didn't study computer science or forgot all the things like I did. Microcontrollers, they have a CPU to do some, arithmetics and copy stuff around in memory. They have RAM typically and I/O so they can connect to the world. They have flash memory nowadays. They used to have ROM, which were only programmable once. Flash memory, it's like a USB thumb drive. You can, upload stuff again and again. So how do they look like? That's an 80 mega. And for comparison, there's a banana, or the tip of a banana. So those things are kind of small, right? They are. This one has 32 kilobytes of flash. The last time I checked, only the text for my presentation is around about 80 kilobytes. Has 2 kilobytes of RAM, so I could not even fit this presentation into that small processor. It runs at, or has a computing power, whatever that means, of 20 MIPS at 20 megahertz. I have no clue. There's something like the Linux kernel shows when you boot it, right? A more modern machine of 2011, so 8 years ago, ARM Cortex A5 has over 1,000 MIPS at a way higher megahertz, right? So it's a small thing. Those are small and bare bone. How would you connect to that? It's like the size of my fingernail. And there are a lot of those pins. You need to connect them somewhere. So not quite convenient. So there's a solution for that. For example, the Arduino platform. I guess many people have heard of that. So the red circle is around that original microprocessor I showed you before. It's practical because you have an embedded USB to serial connector or a converter and that, so you can actually talk to that machine, that processor. You can attach a power supply, so you can simply connect it to your computer. Apple users will maybe need an adapter, of course. There are different variants and form factors, and there are so-called shields for the Arduino platform, which means you can just plug something on top of it with those connector rows on top, you see on top and bottom. For example, I don't know, to control motors, 3D printers, sensors, and all that. There's also the STM32 platform, different manufacturer. It's ARM Cortex and 3-core, a little bit more powerful. You have a lot of options with that processors. Faster and slower, more memory, less memory, but they max out in this example at 1 megabyte of flash memory and a whopping 96 kilobyte of RAM. But you can have them with 144 pins, so assume you can just attach a lot of blinking lights, maybe drive a pinball machine with that. But there are also some which are small and even smaller. You see the smallest one right in the top middle? This is even half or even less than half of the size of my pinky fingernail. It has only 6 connectors, and you will have a hard time soldering it to something. I tried. Still, it's fun. Just to give a comparison, there's also the concept of system on a chip. This means you have a microcontroller, but embedded in the same chip, there's a little bit more like Wi-Fi, some other kinds of I/O connectors, PCI Express, USB, all that. You typically find them in routers, in your Echo Dot, in some whole control appliances and all that. One example are ARM-based systems on a chip. What you see here, that's a Raspberry Pi, actually the Raspberry Pi Zero. It's the size of maybe a little taller or longer than a credit card, roundabout. You can determine there's an HDMI connector and 2 USB connectors just to give you an idea of the actual size of this. But skip that. That's a real computer, right? It runs Linux, and you can attach hard drives and internet and all that. So on the other hand, they are cheap, like $5 for a computer with a lot of processing power and input-output capabilities. That's great. On the other hand, a little bit on the large size for my taste. So I prefer something smaller, which is especially the ESP platform, the ESP8266 or the ESP32. Again, banana for size. Different options. There are the smaller ones and the larger ones, more pins, less pins. And on the bottom, you see one which is interesting because it has an integrated LiPo battery connector. So you can just plug in the LiPo battery and you can run off the grid. Just to get an idea, the actual system on a chip, on the top right module, this small square black thing, that's the actual chip with all the things. Everything around is just a little bit of supporting stuff like a serial adapter and all that. So these are tiny, low power. They run even on battery, but the best thing is they have Wi-Fi. Remember, full stack developers. So let's have me give you a jump start. Beware, a lot of bogus analogies ahead. We need a development environment. There are multiple options how to get your code into that tiny little machine. The most popular one maybe is the Arduino IDE. Has an editor, it brings cross-compilers with it, you can upload the firmware, it manages dependencies, including dependency hell and downloading the internet. It's kind of the IntelliJ idea of Arduino programming on that level. As I said, bogus comparisons. And there's platform I/O, that's more to my taste. That manages your toolchain, provides cross-compilers, firmware upload dependencies. It's more or less like the NPM of embedded programming. You can use it in a shell with your favorite editor, whatever that is. I will not go into details. And you see on the bottom, looks like Node.js NPM tooling, right? It's colorful and things are downloaded and happening and you understand only 1% of that. So when we have a system as a full stack developer, we want to log in. Well, it's actually known as console access. Actually a serial connection. Characters sent over wire to some device and the device answers with textual representation. Arduinos come typically with a serial to USB adapter, so just plug in and you're good to go. It's also the case for many of the other development boards. There are standalone serial adapters you plug into your USB port. These are super helpful if you break your router, a firmware update that went wrong. You can connect to the serial port you will find somewhere after cracked it open and you realize it's just a Linux console, so maybe you can fix it. Takes way more time than just buying a new one, by the way. When we have now this system, we want to connect it to the world, and when we connect to the world, we need to think about data types. There's something like a Boolean data type in the embedded microprocessor world. It's called like digital input-output in the most basic sense. It's yes or no. Well, actually, it's also maybe yes and maybe no. Well, it's high voltage or low voltage, or pull up or pull down. What does this mean? So either there's a voltage connected to that pin or no voltage connected, or it reads high if nothing is connected, or it reads low if it's not connected. You see, suddenly your nice abstraction of binary, encoding binaries as there's voltage or not, kind of is hit by the real world. The same goes when you have Boolean values which are true, false, or nil, right? So we have something like decibel numbers. We don't have actual decibel numbers, but there's something like an analog to digital converter. That means a varying voltage applied to a pin is converted to a digital representation, basically a number. On the other hand, there's no real analog output. A pin can either be high or low, but you can fake it with pulse width modulation, which means you turn it quickly on and off in a certain pattern. So the top line, this is a very professional drawing, the top line should visualize that in this case, the pin is low, low, high, high, low, low, high, high. And on average, it's high 50% of the time. So you have like half of the technically possible voltage. And the bottom case is only high 20% of the time. So you have something like a fifth of the voltage applying. It works. It's surprising. It works. You can even like do audio, like with that story phone. It works like that. Internally, all these things are typically mapped to an integer range of 0 to 255 or something. Depends on the machine. But that's the data pipes only. We'd also need a communication protocol. There's nothing like HTTP WebSockets or well, there is, but basically, there's nothing like that, but we need something to communicate to those sensors. So most common, or one of the most common protocols is serial, sending characters and receiving characters, or sending bytes and receiving bytes over a serial connection. This is used to program most of the microprocessors. It's used for split keyboards, so the individual halves can communicate with each other. There are more products like SPI used to connect sensors, MP3 decoders, SD cards, or memory, for example. When you look at that, it's a little bit when you go down from going from HTTP to TCP, IP, and finally Ethernet. It's less and less software involved, and it's more and more electrical engineering. I like to avoid the electrical engineering part because there's a library for it. What do we do now? We might want to connect sensors. There's nowadays sensors for basically everything. There's switches, push buttons, shake sensors, tilt sensors. Remember pinball machines? They have a tilt sensor. Temperature, you can measure temperature, humidity, pressure, weight, acceleration, magnetic fields, GPS, whatever, moisture, air quality, light intensity. You can attach microphones, cameras, guess what? So you can read data from the outside world. And you can connect something like actuators. LEDs, LED strips, those blinking lights I showed before, or maybe when you paid attention, you could see the magic trash can is blinking from time to time, desperately trying to connect to the internet, which fails. I'm sorry, but it blinks. You can attach stepper motors and servos. Stepper motors are good when you want to achieve precision control over the rotational position. Servers are more like absolute positioning. You know them maybe from aircraft model building and something like that. You can control valves and pumps and even sound. Making noises is always awesome, right? You can connect displays, dot matrix displays, TFTs, and all that. So how does Arduino programming look like? Basically, it's C code with some conveniences. It has some implicit defaults and globals. It provides, for example, contents for all those pin definitions, so you don't remember all the details of the data sheet. It depends, of course, on the microcontroller and the actual development board. But typically, there should be no boilerplate for you, so there's no public static void main. You can just code right away. And as developers, we know, yeah, it kind of works, but eventually there will be boilerplate, sure. How would an Arduino Hello World look like? So technical diagrams ahead. So we connect the pins, say D1, over that should be a momentary switch to ground. So pin 1, ground, switch in between. Can close the connection or the connection is open. When the switch is closed, it's connected to ground. That's the easy part. But what happens when the switch is open? Technically, it's called to be in a floating state, which means there's no defined voltage level. This is why we use something which most microprocessors support, internal pull up or pull down. So we can basically assign it a default value when the pin is not connected. That's handy. And we can use another pin which is connected, again, a very professional diagram, which is also connected to ground, but in between is an LED and a resistor, so we can have light turn on and off. The resistor is to not blow out the LED, and the microprocessors, when you like to look up tutorials and all that, cover that in detail. Warning hat, C has a strange irregular syntax or notation where parentheses do not include function names. It looks a little bit like JavaScript. So a typical Arduino program is structured like having a setup and a loop function. The setup function is executed once, sets up some things. In this case, assigns a pin mode, telling the microprocessor whether you want to read from a pin or write to a pin. We use pin 1 to set an input with a pull up, and pin 2 to be an output. And then we loop. This loop function is called again, so it's looping. And what does this program do? It reads from that pin, and depending on whether it's high or low, it will write to the output pin high or low. So the effect is when I press the button, the light turns on. Super exciting, right? We could just have used the switch directly. Well, timing. We might want to have the button turn on the light and turn off the light 2 seconds later. Nothing harder than that. No, it's actually easy. We write the pin high, then we add a delay. The microprocessors do nothing for 2 seconds, and then we write low. Problem solved. But what if we want to do more things at the same time while the microprocessor is waiting? Nothing else can happen. So unfortunately, we don't have core async, but we have variables. So we just remember the last time we read the pin, and after a certain time, when the time passed over beyond 2 seconds after the last time we detect it's low, we write turn off the LED, and in the meanwhile, there's a millis function that gives you the number of milliseconds since the system booted, so we can convert it to seconds and detect whether it's even or odd, and depending on that, turn on another LED at pin 3 on or off. So we have a blinking LED while we still can react to buttons. That's great, but a little bit unfamiliar to clojure developers, I guess. So what about memory? So bad news first, there's no garbage collection. Well, there is, but not like we know it. So do we manually allocate and dispose memory? Sounds horrible, right? Well, we can work around that. First of all, we can embrace globals. Just imagine that's a top-level atom or something like that. So when we loop here, we just remember the last time called in that global variable. That works. And we can also use the stack. When you have a function, you can allocate locally some data, and magically it will disappear from the stack, the memory, when the function returns. Practically speaking, for the size of applications I do with those devices, I never had any issue with memory management, unless you try to parse some JSON, which can be super huge, but there's a library for it, trust me. So case study, reading that Rotary dial, it's a little bit more complicated. I found this nice hardware, I bought it on eBay, childhood memories. Basically that dial is 2 switches, and the activation patterns like that. One switch goes down while you start dialing, and the other switch only closes for a number of times depending on the rotary dial or the number you dialed. So actually it ticks once more because otherwise you couldn't have the digit 0 on the dial. So how do we read that? It's a little bit more complicated. We wait for the one switch to close, then we loop and wait until we read a low. When we read low, we know the other switch closed. We count the number of ticks. It needs a little bit of fiddling around and training. Unfortunately, we don't have a REPL, so it takes a while to upload that again and again. When we can read a digit, we can read a number by just repeating reading a digit. As clojure developers, we would like to use a transducer to do that, for sure. I've yet to find a way to emulate that, but I don't need to because a simple loop and some local variables also will do. It's a foreign world. It's really strange, but it's super, super nice when it actually works. Nobody comes and forces you to install security updates. So once it works, and it keeps working. When we can read a number with the Rotary dial, we can select a song with that, right? So we can build something like a jukebox, dial a song. That's awesome. We need that play file function. I'll leave that as an exercise for the reader. There's an MP3 module, there's libraries for it. It's super weird, but it works. And what we can build except besides the jukebox is something like Choose Your Own Adventure. And what you heard, which I played in the beginning, was just as a sample, like whatever, you lie in your bed, you feel that itchy tingle in your toe. What do you want to do next? And then either dial A or B. Well, you're not forced to dial A or B. You're just suggested to do that. And depending on what you dial, you get to the next chapters, like those Choose Your Own Adventure books, which did not prevent you from cheating and just going to a random location, right? But that's the whole idea. And it's actually nice and fun to be able to do that, interact with the physical world as a developer, which normally just does something like on computer screens and browsers. Is that full stack? No, of course it isn't. We're lacking one thing, which is internet. It's not full stack without internet. So I bought this vintage-looking voltage meter, put it into a box, and I thought it would be nice to be able to control that over the internet. So I added an ESP8266. You see, it's rather easy. 2 connections, a little resistor. It took me way too long to figure out how to make it work, of course. But let's start simple, no internet involved. What do you want to do? Well, we just write a random value to that pin and the needle should move, right? So, demo ahead. See, this is just for you to see, to be better able to see the device. So ignore it for now. So let's, can you hear me? Yeah. So this is only for you better to see the device, and well, it doesn't work. Of course, you need to plug it in. Retry. It's compiling, it's doing its NPM stuff. Now it's uploading, I guess. And when it's uploaded, we should finally see the needle a little bit moving randomly, right? Not too exciting yet, but it is. So, but we need more tire fire in the demo, right? Let's connect it to the internet. Actually, again, I will fake it because I had trouble connecting it to the internet. But the good thing is those devices can set up an access point, so I can connect to that device. So how does it work? There's a lot of boilerplate, of course. The key thing is that you can start a web server, register a handler function, and in that handler function, it's reading just the query argument, set that as a target value, and in the loop function, it will adjust the needle to be closer and closer to that target value. Why not directly set the target value? Well, the needle will jump around way too fast and overshoot and it's not looking nicely. And when we do this, we want to do nice things, right? So let's try that. It's again doing its Node.js thing, uploading. And let's see, HTTP server started. Nothing happens, of course, because we did not tell it to change something. So let me check whether my computer already connected to that device. Spoiler, it didn't. I think it is. Did you see that? It says something like join. That's promising. Let's set a value by HTTP. You see, I set it like the range is 0 to 1000. Let's just think of another value, 300. Well, that's cool. So I can now send arbitrary values to it. Ignore the response you see from the web server. This thing is not working as intended, but it is, because you can set values, right? And you can do one thing. You can program it to show you actual CPU load. At home, normally this thing shows the usage level of my cable internet connection, which is nice. So I know that it's not the VPN not working, it's one of my kids watching a Netflix show or something like that. So let me try to crank up the CPU load. Well, I did. Let's quick kill it before the machine stops working. It's still high. Did it work? Yes, please really kill. Where's my mouse? Oh my God. There we go. I think we're back to normal. Cool. And we should be able to do even more because, yeah, it's still working. Because now, look, no strings attached. It's running off a power bank. And, well, it doesn't change because I don't sense. The CPU load doesn't change. So, still working. So now we can access all the data, right? So it's great. What do we do with that? So another thing, and that was the inspiration for the title of this talk, is this. Did you remember to put the trash out? I think anybody who has kids know that discussion. And if they change the schedule, everybody is confused whether it's today or tomorrow. When somebody starts putting the trash can out, everybody will follow, even if you're 2 weeks early. So we need a family alert device. We combine Wi-Fi, HTTP, JSON. Actually, we use a Google Calendar to, you don't see the slides, right? It's working somehow. There we go. So we need that family alert device. We use a Google Calendar where we register all the days of like the trash days. We have 3 different kinds of trash cans in Germany, so it's a little bit complicated. And I use those NeoPixel LEDs to gain attention. What you see here randomly lighting up in bright rainbow colors. When you look at the inside, it's a little bit cramped. I had to push in a couple of things, LEDs and that ESP board and the LiPo battery charger. It doesn't look better on the other side. You see it's very technical. It's duct tape and cardboard involved. It survived the airport security check. Nobody got curious. I'm still baffled by that. You can travel with a Rotary phone, microprocessors, a magic trash can to the US, no problems whatsoever. And we look at this from the side, you see those LEDs, those full color controllable LEDs. The thing was, I 3D printed that. Still was a lot of work to get everything assembled in that. And no, I will not build another one. So that's the magic trash can. I still have to figure out how to enable airplane mode because this thing is desperately trying for my home, searching for my home Wi-Fi right now. But Clojure, we are at the Clojure conference. Maybe people want to use Clojure. Well, there are more options actually. You could use Lua, for example. Lua has a good story on embedded systems. There's something called the Node MCU firmware, which supports the ESP family of chips. The syntax is kind of weird. I never got that. That's a personal thing. I don't like it. There's MicroPython. It also runs on ESPs and more systems. It had a nice touch because it offers a web rebel, so you can connect via HTTP or something to your device and execute Python code. It supports something like the Python 3.4 standard. I'm not a Python person, so I don't know what that should tell me, but I take it as, well, this is good. And in that code example, you see you can, for example, connect those DS8020 sensors, which are temperature sensors, iterate over all of them and read the temperatures. I tried that at home with my floor heating system, which was a little bit off. I spent more time getting those sensors connected and running than actually fixing it. But, you know, that's what we do as software developers. It's escalating quickly. There's Ferret. Ferret is interesting. It's the Lisp compiled to C++11, whatever that means. But I know there's a C++ compiler for all those systems I use. It actually supports many of the devices and platforms I've presented so far. Arduino, for example, that 80 mega 328 chip, ARM devices, ESP devices. It has kind of a sane syntax. I think Rich would be pleased, right? So it's S expressions. It uses that weird require logic to import stuff. It has that forever loop. Clearly a concept which is missing from clojure, right? And actually it supports native calls to C and C++, which allows us to use all the libraries for sensors and actuators and all that. And there's another thing, there's Toccata. I learned about that at the conference. It's a Lisp compiled to C. Once again, seems to be a good concept. It looks like it has the same syntax though. I have not tried yet to compile that to Arduinos and ESPs, and to my knowledge, nobody ever tried before, but technically there should be no problem doing so. Famous last words. Yet, I haven't tried that. Ask Jim Dewey, he's at the conch, I don't know if he's around right now. There he is. Yeah. Maybe we can make it happen eventually. Then there's JavaScript. Yes, you can run JavaScript on some of those devices. There's the Arduino firmware. It runs on ESPs and also on the STM family of chips. And very interestingly, it also runs on the NRF52832 chip, which is a Bluetooth low energy system on a chip. So you can create Bluetooth devices, for example, keyboards. And you can buy full, like small development boards, which are self-contained again. But now that we have JavaScript, everybody is already thinking of the same thing I thought. ClojureScript, right? I tried. Well, a minified Hello World was still in the range of 100 kilobytes. And just remember, some of those devices have 2 kilobytes of RAM. So I'm not a ClojureScript expert. I didn't dare to ask David Nolan for help. Well, it kind of loaded in the Arduino on an ESP for over 30 minutes. Did you ever hear of the halting problem? I'm still not sure if it would ever either crash or stop. Where do we go from here? Learn you some microprocessors. This is really fun. This is outside of what most of us do daily. Machine learning, data analysis, building business enterprise-y CRUD web pages. I don't know what people are doing here, but well, I think only few of you would do hardware, right? And it's easy. Go to arduino.cc. There you'll find hardware, libraries, tutorials, a great community telling you how to do things or how not to do things. Or you can go to Adafruit and buy hardware. They have libraries, tutorials, and a great community. You can go to SparkFun, for example. There are no affiliate links for that, by the way, so it's just like what I like. I personally go to AliExpress to buy cheap and then finding out it doesn't work. On SparkFun, you will get hardware, libraries, and tutorials. So what should be your takeaway? If you don't know it, learn it. That took me kind of like 3 years, not to master, but just to be at where I am right now. But buy an Arduino, go read some tutorials, make some lights blink. That's already fun enough. And it will tell you something about your everyday life as a software developer. There's not only the holy grail of closure, persistent structures, hammock-driven development. It's also the effort-driven development, because you follow the tutorial and it doesn't work until you find out. You need to plug in the plug, right? And actually what you do is Google-driven development. Well, which is the mantra of modern software development anyways. Just one advice: avoid mains voltage. Really, really avoid it. I tried when I was younger. And there are modules and devices where you can safely control that. Think of the whatever Philips Hue light bulbs and all that. And there are other devices where you can which you can plug in a socket and control by Wi-Fi. Don't buy it cheap from a random seller in China or Canada or whatever, Mexico. Go to an authorized dealer, ask your local electrician or whatever is responsible. No kidding. And now, go and tinker. Thank you.